Hello, my people. Hope we're doing well. This is the third and final installment for this series of videos on Newton's method. In the first one, we talked about linear approximation. We reviewed it really quickly because Newton's method is a second strategy for approximation. We then went through a couple of Newton's method iterations the long way. We derived the formula. In the second video, we did a couple of examples using the formula, and then of course talked about the second application. We could actually use it for many of the same reasons we use linear approximation, and it winds up being a better process, largely because it is iterative, and we basically can do it again and again and again and again and again until such time as we actually find the decimal approximation that the calculator would give us, functional. In this video, we're going to talk about when Newton's method fails. And in large part, I just want you to know that it can fail, and it can fail for at least two reasons. Now, the first example we're going to use is the sine function. Okay? And we know that if f of x is equal to sine x, then f prime is cosine x. And we see that the original function, the sine function, looks something like that. Okay? Now, I have intentionally not scaled the x-axis according to measurements of pi, which I actually can do, and you can do in Desmos. But I've done it this way because I'm not looking for an exact value. I'm basically looking for an approximation of the zero, and I'm using this particular function because it's a training wheels exercise, okay? Now, let's go ahead, and we know that if we eyeball it, we see that the first zero, the first positive zero, is somewhere right about 3. So we're going to use 3 as a x sub 1, okay? So let's go ahead and let's go ahead and plug this in, and we see clear, go sine x, boom. Okay. Now let's go back to the home screen, and we recognize the fact that 3 is our first approximation, our x sub 1. And then I'm going to go up and I'm going to grab my formula, and I'm going to press enter. Now what has happened here, of course, is this has become 3 minus sine of 3 over cosine of 3. And that is going to give you approximately what the calculator gives you is 3.1425465667. Now this value right here goes into here, and I'm not going to do the whole thing. I'm just going to do an approximation of that because, not enough room there. And that's going to be 3.143, which is of course shorthand for that actual value, minus sine of 3.143 over cosine of 3.143, and that has given us 3.141592653. And, if you're going to, you could have done it like, that stores into A, and then you could kind of put A here instead, right? So let's go ahead and store that into B, and if B is here, then it's going to be B minus sine of B over cosine of B, and that's going to give me my next approximation. So if this is a sub 1, this is a sub 2, this is a sub 3, what goes out here is a sub 4, so 3.141592654. Let's go ahead and put that in as C. So it's C minus sine of C over cosine of C, and that only changed in that last decimal place, in that 9th decimal place. So it's obvious that this is going to be the new value. This is going to be exactly the same value on the next iteration because it will not have changed, and that right there is our approximation. Now, we've seen pi enough times to know that that actually is a really good approximation, right? And if we actually go to our calculator and we press pi in here, we're going to get exactly the same thing. Now, that actually did work out, right? I thought, we're going to talk about, times and the patterns for which it actually doesn't work out. But it did work out because it was an approximation that was sufficiently close. Let's pick one that's not sufficiently close. Let's pick 1.8. Now again, 1.8, like I said down here, as an estimate is ridiculous, but this exercise will actually prove a point. It will illustrate the fact that in order for this to work, it has to be something sufficiently close. So when it fails, it is a possibility that in your haste, you looked at the graph and you plugged in, you go, oh, that's right next to the 3, so I'll plug in 3 as my x sub 1, and you didn't count correctly. It's actually next to 4 or something like that, okay? So when it fails, the first thing you need to ask yourself is, have I chosen something? Have I correctly chosen my x sub 1 so that it is sufficiently close? Because watch what happens with 1.8. Boom. That's not close, okay? What's going on here is basically the curvature of the graph has sent this closer to the second positive 0 at 2 pi, right? And what's going to happen, because this winds up landing near 2 pi, as you do it iteratively, you're going to get values that are closer and closer there. Now, that's not necessarily a bad thing if you're looking for any 0, but if you're looking for a particular 0, yeah, that's a bad thing. 85301, and then you do it again, and it winds up being 6.283185307, and that only changed in the 9th place, so it's obviously going to be that at the end. That is our estimate, okay? And that actually is a great estimate for 2 pi. It's just not a great estimate for pi. Okay, so like I said, it can fail. Sometimes it's going to be your fault. Let's look at another example where when it fails, it is not your fault. But first, I want to give you a graphical sort of picture of why that second one failed. The first one was basically a tangent line that started here, right, at 3, and then went ever closer to that 3.14. This started here at 1.8, and because of the curvature of the graph, it shot out over here and started making tangent lines that would approximate this 0 over here. So that gives you a visual representation of kind of what we were doing when we were playing with that, okay? Now, the Newton's method can fail for reasons, what my old principal used to call a picnic error. But picnic is when the computer glitches, problem in chair, not in computer. But similar to that, right? Here is a time when basically Newton's method will glitch for reasons that are beyond your control. Now let's consider the parent function of the cube root, functions, okay? Now you know where the 0 is, but let's just play ignorant this time to illustrate a point, and let's estimate the 0 at near 1/2. Because what happens if we estimate it near 1/2 is this. Let's go ahead and and we can go to math and do it here as the cube root of x, or of course you can plug it into y1 as x to the 1/3. It doesn't really matter. Let's go ahead and go out here, and let's say 0.5, and then let's go up and grab our formula. And what happens is when you plug in 0.5, you're going to get -1. And then you're going to get +2. And then you're going to get -4. And then you're going to get +8. And then you're going to get -16. Now, the reason why you're getting decimals like this is because of just the imperfection of the algorithm that the calculator has. But if you actually did it by hand, you would get exactly these values. That doesn't look like it's getting closer to the 0 that happens at the origin. In fact, that looks like it's getting farther away, twice as far away each time. It seems like that each estimate is being multiplied by -2 in order to get to the next one. And actually, it is. So let's actually look at why that is. Okay? So if we have x sub n is equal x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of it, yeah, our formula basically, we can actually plug in the cube root of x sub n as our f, right? And 1 over 3 times the cube root of x sub n squared, which basically, gives us the cube root of x sub n over 1 times 3 times the cube root of x sub n squared over 1. And that means that what you're getting here is x sub n minus 3 times x sub n, and the arithmetic there is very simple, negative 2 x sub n. Now that shows us analytically why each successive each successive estimate is going to be times negative 2. But just look at the graph. Can you actually find a point on that graph where the tangent line is actually going to get you closer to the 0? And the answer is no. Okay. So sometimes there are just times when the Newton's method fails, and that's fine. That kind of brings us to the end of this. I mean, the main reason I want you to know that it can fail, and the two reasons why it could fail, is I don't want you to get, first of all, when it fails, I want you to go back and check your work. But if you go back and check your work and your work is fine, I need you to realize that sometimes it does fail, not because of anything that you've done, but because it just fails, okay? Now, that brings us to the end of our third video. I hope these videos have been helpful and instructive for sort of laying out Newton's method. If you have any questions, obviously you need to email me or ask me in class. Bye.